All right, we're going.
All right, so thanks for coming. Thanks for the introduction, and to go on for inviting me to speak. Today is my first day here in Rutgers for the next 3 years, so I've seen you around, and it's great to start like this. So I'm going to tell you about an ongoing project that has been linked to various different papers that I'm writing with various different people. And it also has a nice experimental side to it, which I'll get to in the end. Where when I mean experimental, I don't really prove things using experiments. I sort of find more questions using experiments. So let me begin with the basic object that we look at. So these are colored sequences of partitions. So what do I mean by this? Let's set, for example, I to be the unit interval in R, and we fix a parameter alpha between 0 and 1, and a substitution rule which takes the unit interval I and replaces it with two rescaled colored copies of I. Okay, so one of them, as you see, is alpha I to the left, and 1 minus alpha I, the blue one, to the right. And here in this picture, alpha is 1/3. And we construct a sequence of partitions using this substitution rule, using the following splitting procedure that was introduced by Kakutani in the 70s. So you put the trivial partition pi 0 to be just the unit interval, and you define the m+1 partition by substituting all the intervals that are of maximal length in the mth partition. So let's see what it looks like. So this is the first partition. Now the blue one is bigger, so we substitute this one. And the blue one is still bigger. And now the red one is going to be bigger than the blue, and then the blue and the red are the same size, and so on and so forth. So once again, you always break the biggest stick. That's the point. Okay. So if we call the set of left endpoints for all the intervals xm, and the red intervals rm, and the blue intervals bm, we can ask various questions about this sequence of partitions. So the first type of questions concerns uniform distribution. So is the sequence of left endpoints of all the intervals that appear in these sequences of partitions, are they uniformly distributed? And is it also true if we only look on the red and the blue intervals? This is one type of questions. And the second type of questions is about frequencies of colors. So a first frequency would be, does the ratio between the number of red intervals and the total number of intervals, does this converge? And does the measure of the red set converge? So obviously, given a point, it changes colors infinitely many times. But you can still ask about the volume of the entire red set. So let's just think about the case of alpha equals 1/2. What happens with alpha equals 1/2? You break it, half. Oh, two of those, to the two intervals you get maximal length. So you break all intervals, you get fourth, etc. You always break everything. And obviously it's uniformly distributed, this sequence. So the number of red intervals over the total number of intervals will always be 1/2. And the measure of the red set will always be 1/2. So we get exactly the same limit. Is it always the case? Okay. So we'll see about that later. This kind of construction can be generalized into higher dimensional or maybe more complicated constructions in the following way. So this is what I call a multiscale substitution scheme. It consists of a set of prototiles, in this case a rectangle and a square, and a substitution rule which gives us a way of substituting the prototiles by patterns that are all made up of rescaled copies of the prototiles. So you can see I replace a rectangle by one rectangle and 3 squares, and I replace the square by 2 of each, and the scales are not, there's no uniform scale. I use various different scales. And you can do, you can define a sequence of partitions in the same way using the same Kakutani splitting procedure, replacing length by measure. Yeah? So for example, if I start with a rectangle, I substitute it to get the first non-trivial partition, and then the biggest tile is the square, so I substitute the square, and then I see this rectangle at the bottom. Now it's the biggest one, so I substitute that, and I get this very nice sequence of partitions.
Beautiful.
Yeah, I really like it. I still like it. Okay, so.
Do you have more? I mean, what does it converge to? You don't.
So I don't have, so okay, what I should tell you about these pictures that they look so nice because I've done them in a kind of a designer software. So this is not a mathematical software. So this took a long time, and my wife used to be a designer, so we sat and we did all this with a calculator actually. So this is a bit old school. What does it converge to? Well, it doesn't converge essentially to anything. But you can ask about if you pick, I'll show it in a minute, if you pick a point in each tile, does this thing uniformly distribute? And you can ask the same kind of question that I asked before about these frequencies. How much yellow do I see? How many squares do I see? Etc. And these things we will see that they do converge. Okay. So a very convenient model for the substitution schemes is the directed weighted graph model. So what do I do here? I take a substitution scheme and I build a graph in the following way. So the vertices of the graph are just the prototype. So here there is one prototype, the unit interval, and I have one vertex. The edges that originate in a vertex that is associated with a prototype, as I said, model the tiles that appear in the substitution pattern that appears. So here I have the unit interval, and it has two sub-intervals as a substitution pattern, and this corresponds to having these two loops, one blue, one red, and the lengths of these loops are determined by the scales of the tiles. So scales is multiplicative, and paths and graphs are additive, so you take a log. And since log of third is a negative number, which is not a good thing to measure length, so I take the minus. But essentially, this is the whole thing. It's nothing very complicated. Okay? So we say that a scheme is irreducible if the graph is strongly connected. And these will be the examples that are interesting to us because, for example, if we take this kind of scheme over two labeled intervals, so this might not say much, but let's look at the example. So first you take the unit interval and you substitute it according to the left scheme. So it's 3/5 and 2/5. And now you only use the second scheme and you always just substitute each one of them into a half. So what in fact you get is after you get the 3/5, 2/5, now the biggest one is the 3/5. And now the biggest one is the 2/5. And now it's that side, and that side, and that side, and that side. See? So you are not going to get uniform distribution, because half of the points are in this 2/5 and the other half in the 3/5. So these are kind of the bad examples that we are going to ignore. And these are the uniform distribution results. So the theorem by Kakutani from 75 was concerning these alpha Kakutani one-dimensional sequences. And he shows that for any alpha, the sequence of endpoints of all intervals is uniformly distributed. And the way that he does this is using ergodic theoretical tools, showing various things about the invariant measures and so on. This is not the way that I kind of look at these kind of problems. And my generalization of this result, which holds for any dimension and any kind of substitution scheme, is exactly the same. I just have to assume reducibility. And by uniform distribution, I mean the following thing. You pick a point at each one. You have this nice kind of family of sets of points. This thing has to uniform distribute, which means sort of that if you put a delta measure and normalize this, this converges weak star to the Lebesgue measure, to the normalized Lebesgue measure. Okay? Evenly spread. Okay. So the way I model these partitions on the graphs is using what I think of as a continuous flow on the edges. So in my notation, a metric path is just a directed walk on a graph, but it can end anywhere. It doesn't have to end in a vertex. So usually paths are walks that go from vertex to vertex. But I say a metric path is just a walk. You start somewhere, you walk along the edges, and you stop. Okay? And the point is that the tiles that you see in the nth partition, they can be modeled by the set of all metric paths that have a certain length. So this is how I think about this. In this example, the 1/3 Kakutani example. So the trivial partition is just the unit interval, so it corresponds to paths of length 0, and there is exactly one, it's the trivial path. Now I start to walk to all directions that I can on this graph from this vertex. So I can either go left to the blue loop, or I can go, that's right, to the blue loop, or left to the red loop, right?
It's a directed graph?
It's a directed graph. So I walk until I hit another vertex. So the blue loop is of length log of 3/2, because that's what you get out if you take the log of 1/2/3. So I hit the vertex, and the other path that started to go to the other loop did not finish. It stopped somewhere in the middle. And indeed, you can see that I have one. How do I do this? This, yeah. I have one blue segment, one red segment. It corresponds to one blue path and one red path. Okay. Yeah. Now I continue this way. So now I'm going to have a continuation of this red path, and this blue path is going to have two continuations. One in which I again choose the blue, and the other where I choose the red. And this is how it looks. Again, I hit the vertex. So it's 2 times log 3/2. That corresponds to this 2 choices of 2/3. One loop of 2 of the blue one and then going to the red corresponds to the choice of first 2/3 and then 1/3. This is this one. And the original 1/3 still did not get home. But this is the next one, because after 2 log 3/2, the next one is going to be log 3. Okay? So we're going to have more. All right, so this is how I model tiles and partitions using metric paths. And the way I described it, you get that the number of red endpoints or red intervals is just the number of metric paths that are of length Lm, which terminate on a red edge. And another thing that you can also see, I'm going to kind of really say this quickly. If you take your graph and you add probabilities to outgoing edges, for example, in this case, I would add a probability of 1/3 that I go to the red one, and a probability of 2/3 that I go to the blue one. This corresponds that 1/3 of the points are red, and 2/3 of the points are blue each time I do a substitution, right? So if I add these probabilities, I can also calculate the probability that the metric path of length Lm terminates on a red edge. And this would be exactly the measure of the red union of red intervals. Okay? So you can believe me, or just think about it for a second, but this is just like an observation that one can make if he thinks about this for long enough. So essentially, these counting problems, can be approached using counting on graphs. And since uniform distribution can also be understood as a counting problem, so also uniform distribution can be approached using these counting on graphs. So what you need to know is how to count on graphs. Okay, there are 2 kinds of graphs. A graph can be incommensurable and a graph can be commensurable. So incommensurable, or a scheme is incommensurable, if the graph has 2 closed orbits, 2 closed paths, maybe I could say, that the length is incommensurable. That is, the ratio of the lengths is not a rational number. So if you think about a classical graph that's not weighted, and you think, okay, I just say that every edge is of length 1, then obviously all closed paths are integers, and all ratios are rational. Okay? But this is not the case in a general directed weighted graph. So my theorem says that these sequences of partitions that are generated by incommensurable schemes have the color frequencies. Okay? And not only that they have the color frequencies, these can actually be just calculated explicitly in terms of the graph. Or in terms of the
for your first example,
yeah.
1/3 and 2/3. What are A and do the A and B have the logs in them, or are they?
Yeah.
So what's A and B for that? For your first example?
Great question. So one would be log alpha, or minus log alpha, and the other would be minus log 1 minus alpha. So if you plug in alpha here equals 1/3, for example, and you just get rid of the minuses, then you get that the question you ask, is log 3 over log 2 essentially, is it irrational? And the answer is yes. So in the 1/3 example, this is an incommensurable example. But of course, there are infinitely many alphas for which it is commensurable, but generically it's incommensurable. So, for example, sometimes I ask the audience to guess what the answer is. I don't know if anybody wants to guess. I say I won't pressure you. But for example, think about the limit of the number of intervals which are read over the total number of intervals. There is this heuristic that you can come up with. Think about thirds and 2/3. So, okay. So every time we have a new substitution, the blue one is going to be of length 2/3, and the red one is going to be of length 1/3. So the blue one is twice as big as the red one. So I will probably substitute the blue one more times. But every time I substitute the blue one, I win a blue and a red. So I actually add a red. So heuristically, I can convince myself that there should be twice as many reds as blues. And this is actually true. So 2/3 and 1/3. Okay. But now now we have a heuristic. So you try to also apply it to the measure of the red set. And, well, I'm not sure. But you get something which looks like the contribution to entropy. So the total entropy is in the denominator, and sort of the red contribution to entropy is in the numerator. So there should be an explanation to this, but in any case, this is actually what you get. Okay. So let's see some more examples about commensurable and incommensurable constructions, just so you but so I can. It always feels as if I look at incommensurable construction and say, these are the interesting ones, and the commensurable are rubbish. But it's actually not the case. So for example, this beautiful construction of the Rosy fractal is commensurable. So here you take this thing and then dissect it to 3 rescaled copies of itself, and the boundary is supposed to have fractal boundary. So it's supposed to be fractal. But the scaling constants here are just tau squared, and tau third of this Fibonacci constant, which is like a solution to x to the third plus x to the x squared plus x equals 1. And when you take the logs, you just get log tau, 2 log tau, 3 log tau. Of course, every closed path on this graph is an integer times log tau. So when you take the ratio, just get a rational number. Another nice construction is due to Lorenzo Sadun, and his is the generalized pinwheel scheme. So you fix this this kind of triangle, and you fix those right angles over here, 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 and everywhere, and you just play around with this theta. And playing around with the theta changes all the rest of the thetas as well, of course. So what you always get 4 same scaled triangles and one that is of different scale, and you can play around with it. And for almost every theta, you get an incommensurable construction. If you pick theta to be arctangents of 1/2, you find, then all triangles are of the same scale exactly, and what you actually get is the Conway and Radin's pinwheel tiling, pinwheel substitution scheme, which constructs the famous pinwheel tiling, and if you don't know it, then here it is. It's amazing. Okay? So even the classical commensurable case already gives you something which can construct very wild things. This is an aperiodic tiling of the space, and it has many very interesting properties. Okay, so as you can see, I keep talking about tilings. So the original motivation for this whole project was actually the work that I'm still doing with Yaar Solomon from Ben-Gurion University in Beersheba. And what we actually do is we take an incommensurable scheme, and we take a prototile and we normalize it to be a volume one. And we define this substitution flow that I think of as a continuous flow. At time 0, I substitute the time. And I start to increase everything, to inflate everything. And whenever a tile gets to a volume 1, I substitute it according to the substitution rule. So you kind of get bigger and bigger patches, and you can define tilings of the entire Euclidean space as kind of special partial limits of these patches, these generating patches, and we study two main objects. So first we study the tilings themselves, which may have types and scales and repetitivity aspects to them, and patch frequencies, and are they equivalent, by Lifshitz equivalent to lattices, are they bounded displacement equivalent to lattice, etc., etc. These are geometrical questions. And another type of question that we approach is the dynamical properties of a tiling dynamical system. So essentially, you take a tiling and you can think of it, you have to prove that this is the same thing, but in fact it is. You take one of these tilings, you shift it around by vectors of Rd, you take a closure with respect to the correct metric or topology, the Chaboty-Feld topology of closed subsets of Rd, and you get a space which is compact. And we can look at minimality, we can look at invariant measures under this action, etc. But I won't go heavily into it. I'll be here for 3 years. We can talk about this many times over. But just to show you, so this is not going to be continuous because this is not a film. But imagine this as a continuous thing, and you get like tilings, which are kind of wild. Everything is, all you can see is squares, but the squares appear in more and more and more scales. So there is, in some way, okay, it's just squares. It's easy, but in another sense, there's infinitely many scales. Infinitely many scales of squares. You can ask various questions about these.
The central square seems to have, is it 12? 16 neighbors?
This has 16. Yeah.
4. Yeah.
So if you
does that increase as you keep going out, or is 16 fixed? Is it always 16?
16 is the substitution rule.
Ah.
So every time you substitute a square here, you see, now you substitute a bigger square, but you also substitute another square inside. So you're always going to have these coronas of 16. But you've got to get them in more and more and more scales. And you can color them for your fun.
So I'm quite interested in how many squares in each shell.
Oh yeah, so these
you probably know them.
Yeah, so you can really count these things using the graphs. So yeah, and you can actually do more. You can actually prove more things. It's just you can really prove patch frequencies and so on. Like if you fix a patch that you like, and you want to know how much of it you see around, and you can average it on not only on balls, you can average it on wilder sets like Van Hoven sequence of sets. So yeah, okay, but this is not.
Could you go back? Let me just see if I colored one again. Yes. Yeah.
Why did I color it this way?
No,
It's just nice. Yeah. I mean, I told someone niece did it, and I told her I'm showing this around the world. So she's very good. Yeah, I helped a bit. Okay, right. So let me just say very quickly about the commensurable case. That, as I said, is very interesting. It includes famous constructions such as the Penrose-Robinson substitution scheme that generates the Penrose tiling. But everything that you want to know about this follows from Perron-Frobenius theorem. Okay, so you just put in these. You can really count everything by taking matrices, taking powers of the matrices, and understand everything. So, although this is uniformly distributed as a sequence of partitions, the color frequencies do not exist in the commensurable case in general. It can exist, but it does not have to. The incommensurable case is different completely. And I'm just going to go very quickly on the graph counting result. So I build a graph matrix function, which basically the ijth entry of this graph matrix function is this exponential polynomial with exponents, the length of the edges from vertex I to vertex j. And this is the theorem. This is joint work with Avner Kiro, who is now in Weizmann Institute, and with my father, Mrs. Smilansky, who is also now in the Weizmann Institute, and with myself, times 2. So if you take a graph which is strongly connected and incommensurable, then there is some lambda, and there is some matrix which has positive entries, such that if you pick one edge on this graph and assume it has initial vertex h, then the number of metric paths of length exactly x from some vertex I to this edge grows as this function here. So you say it grows exponentially in lambda. Lambda is the parameter, and the coefficient is given by this thing, essentially. So this is only a function of the graph structure and of this lambda that we show exists. I want to say, though, that this looks maybe a bit horrible, but in the case of graphs that are associated with substitution schemes, in fact, this lambda is always just the dimension, and this matrix, all its rows are identical, so it does not in any way, it does not depend on I, on the initial vertex that you start with. It doesn't matter where you start from on the graph, everything is going to have exactly the same frequencies. And this is the key to uniform distribution.
And the ADJ is adjacency,
And
not adjoint.
Adjugacy. Yeah, the adjugate. The maybe it's called the canonical adjoint, classical adjoint. It's this something matrix. It's this thing that appears. Yeah, it's a transpose of the cofactor. Yes. Okay, so how does this thing get proved? This thing get proved, just in a few words, this thing get proved in the following, using the following technique. So using the Wiener-Ikehara theorem, which is, the Wiener-Ikehara theorem is a Tauberian type theorem. It was used to kind of solve the prime number theorem using maybe as a world record of the least information about zeta that you need. So what is the least information about zeta that you need in order to prove the Wiener-Ikehara theorem? Well, you just need to know that there is a pole, a simple pole at s equals 1, and there are no other poles on this real part s equals 1 line. That's the only thing you have to know, and to the right of it. You don't have to know Riemann's hypothesis about all the poles are actually on real part s equals 1/2, and you don't need any zero-free region that people have been pushing throughout the last century to get better and better error bounds. You just need this thing to get the prime number theorem. And the way that what you actually need to do to apply this Wiener-Ikehara theorem is you take your counting function, which in our case is the graph counting function, and you take its Laplace transform, and you study its poles. So you essentially have to show that these poles do not, that there exists, what you have to essentially show is that there exists some lambda, real lambda, where there's a simple pole, there are no other poles to the right, and there are no poles on the real part S, real part equals lambda. Okay, so in our example, the Laplace transform is just this thing. So this is something, and this is something, and this is interesting. Okay, this is the determinant of I minus ms, I remind you, MS was the graph matrix function. Its entries were exponential polynomials. So I minus MS is a matrix of exponential polynomials with entries of exponential polynomials, and the determinant is an exponential polynomial. So you have to study those zeros of exponential polynomials. Now, as I said, there is always a zero at s equals lambda, and none to the right. If you assume incommensurability, then you have no other zeros on this real line. And in fact, you have infinitely many zeros in every vertical strip. But you look a bit to the left of this line, you have infinitely many zeros. I will show pictures in a second. And information on the location of the zeros closest to this real part of s equals lambda, to this line, can be used to obtain upper bounds of the errors. So again, if you just want to know asymptotics main term of the growth, you only need this. If you want to pull some more information about bounding the error terms, then you need to know this. Okay? Right. So this is another thing that we're doing these days, and this is where I come to the experimental aspect of this work. So we're trying to look at these special exponential polynomials and to study their zeros. So I'm doing this together with Avner, again from Yaar Solomon Institute, and Alon Ishli and Aaron Venman, who are now in the Tel Aviv University. So just as an example, let us look at the alpha Kakutani scheme. So alpha Kakutani scheme, the determinant of this identity minus m of s is just 1 minus e to the minus as, not minus as, minus e to the minus ps. So it's this kind of exponential polynomial, with alpha being log of 1 over alpha, with a being log of 1 over alpha, and b being log of 1 over 1 minus alpha.
They're 2 by 2 matrices?
It's a 1 by 1 matrix, actually. Because you only have one prototype, unit interval, so you only have one vertex in the graph, and you have the matrix is one. So incommensurability is equivalent to this, as we have seen before, to this ratio of log alpha and log 1 minus alpha, which I call beta, to be just an irrational number. So if I change the variables and replace s by z like this, then in fact what we do is we reduce to looking at roots of these kinds of equations. E to z plus e to beta z equals 1. Okay, where beta is this kind of thing. This kind of an irrational thing. Okay? So initially what interested us was to look at this rightmost part of the zeros. What happens next to this critical vertical line? Because then we could pull more information about bounding errors and get discrepancy of the sequences and so on. But pretty quickly we found out that in fact the global structure is interesting in its own right, and I'll show you the pictures. Now all these pictures are of course approximations done with rational polynomials which can actually be solved. And we have done we've played around with it for a while until we found a good way to calculate these things. But essentially what we do, we look at some compact strip. So always these kind of polynomials, all their zeros are always going to be in a strip. This is a well-known result. And we look at the strip and we bound the height of it. And we start to play around with the betas. So this is like a consumer alert. More questions than answers, okay? So the first thing is the golden ratio. So golden ratio is well known for being the best number in various senses. So in the sense of the fundamental approximation, it has kind of the worst approximation, and it has the best when you write an irrational number as this 1 plus 1 over 1 minus 1 plus continuous fraction. Thank you. Is the best continuous fraction. And dynamically speaking, if you rotate mod 1, then it gives you sort of the best evenly spread sequence of points. So this is how it looks to the most right. So here you see this is 1. And this is 0.95, so and this is 10,000, and this is minus 10,000. So you see a very nice strip. It has some structure. When you zoom out, you see that it has a very nice structure. It's very nicely somehow put together, and you can look at it and you can actually see curves and you can see parabols that build up this structure. And you can also look at the histogram of these zeros, and you see this very kind of very low somehow. So everything seemed to be happening in the sides. Okay, now let's take a less nice number, e. And here you can see that there are beginning to be some holes. You can see some holes, like between the points. And when you zoom out, you see, well, it's still nicely spread, but at least maybe slightly less. But the parabols are becoming somewhat clearer. And the histogram was still mostly on the sides, but it grows in the middle also. Now take pi, which is a very strange number, and you can really see the parabols now. But when you look back, you see this beautiful thing. And again, this time it seems that there are, I think here there were more zeros to the right, and here there are more zeros to the left. Okay? And my favorite one is the Liouvillean number. So we pick the Liouvillean number that is in Wikipedia for Liouvillean number, right? And we look at the rightmost, and here I took all the way up to 30,000, not 10,000. And you can see this crazy parabol coming in. When you look back, well, you don't really see anything. And you don't even finish, you have to go all the way maybe to 60,000 to kind of finish this this region without any zeros, and all the zeros are very densely packed along these parabols. So when you do the histogram, you kind of get these holes because you didn't go high enough. But obviously, if you go high enough, everything should smoothen. And there are in fact theorems, I don't know exactly by whom, but in all these cases, when you project to the real line, you get one integral. The closure of the projection of the point.
That picture of the cylinder, it looks like the projection of the cylinder.
It does.
Is it? Is there a glass tube that you're looking at from the side?
Maybe. I mean, this one also, this is like the parabols do the trick. Yeah. Really, I don't know. I should say that most of these, we've been playing around with these things for a long time and trying to prove things, but our effort to make beautiful pictures was because the one asked me to talk here, and I said, okay, let's go experimental. It's a good chance to try, and we were surprised that how nice it looks. Okay, so after we've done with the Liouvillean one, we try to extend it slightly. Now, for a computer to solve exponential polynomials with various exponents, it's not an easy task. So we went one step. So you take e to the z, e to the beta z, and e to the gamma z. You can think, so this can be a model for one vertex and three loops. So you just take a unit interval and you set it into three parts, and you do it again and again. If you do something wilder, like my squares and rectangles in the beginning, the polynomial will also have minuses and so on. Things become a bit more complicated. Okay, so what do we see here? So this is what you get. So again, beta, so the first exponent is always taken to be 1, and we picked also the second one to be 1, or maybe 2 actually, maybe I have an error here, maybe it's 2, and the third one to be the golden ratio. And what we see is that as if you have two patterns, you kind of just put them side by side and a bit intersecting. And the histogram tells you that this is sort of what you've done. But in this example, as you can see, 1 and beta again here is supposed to be 2. So as a set, the exponents 1, 2, and golden ratio, well, they're not linearly dependent over the rationals. So what happens if you take a linearly dependent triplet? So this is square root 2 and square root 3, and again, the third one is always 1. So here you can see that there again, there's as if there are two regions. It's not clear that it sits on each other, but kind of two different regions. The histogram gives you maybe if we'd gone high enough, we'd get one peak. And of course, you always have to plug in the e and pi, and you get this beautiful thing. So I call this the pi part. I don't know why. Maybe this doesn't have anything to do. Maybe this is the pi part. But you can see that you have these rhombi, like socks, right? Socks patterns. And you have to squint, right? But you can see them. And I guess when you have better approximation. So again, when you try to approximate simultaneously both e and pi, you end up with pretty bad approximations. The finite approximation becomes very hard when you go high dimensional. And approximation is not as good. The Dirichlet theorem for the finite approximation, the error term gets worse the higher dimension you go. But here you can really see that it seems to have one peak. Maybe not. Maybe it will grow. Maybe this one will grow, and again you have this two balls together. But we think that if you're able to pick a triplet which is somehow really badly approximable in a real way, then you'd have only one peak. That's kind of what we think, but again, we don't know. This is just looking at things and kind of guessing and asking questions to solve, or at least to show people in this project. Okay, so this is all I have to say. Thank you very much.
Do we have questions?
Are there like computer implementations of these tilings anywhere?
Computer implementation.
Yeah, that will like automatically generate these tilings, or did you have to draw
I
all these
did
by
it.
hand?
I'm not very good with computers.
Okay.
So what I think, so all these things I did by hand, also because I really wanted to. I mean, these were made for presentations and not for work. So there are some people who are better at this, and I promised them that when I figure things out, I would send them some types of tilings, and they will generate them. There's a tiling encyclopedia that is maintained by some people in Bielefeld, which is really nice, and these guys know how to do nice things, and also I should send them these already. They are very nice constructions. So for example, one of my favorite ones that I did not implement yet, that is a generalization of a well-known example. You pick a square and a right triangle, and you kind of, I can draw it in a second. So you kind of do this, this kind of thing. So sort of, right? You get another square here, and you get these triangles, and the triangle is dissected in this way. So you get the same triangle in different scales, and the rectangle square is here. And if you just play around with this angle, you get different things. So I really want to build an incommensurable tiling generated by this scheme. I think it would be just beautiful. But I haven't got around to doing it. So as you've seen, even it's funny, there's something that is kind of universally pleasing in symmetry that is not really symmetry. I mean, if I'd shown you here just a grid, who cares, right? But this thing, which is completely symmetric and everything is squares, but you have all these scales coming up. So this has potentials, coasters and so, yeah. I will get around to it.
Are there any other questions? Let's thank our speaker again.
So you've got one center, distinguished point in the center, right?
Yeah.